In this video, we are going to start graphing polynomial functions. And the first thing we'd like to do is find the x and y-intercepts. The y-intercepts are pretty straightforward. The x-intercepts can take a little bit of work. We're going to recognize the characteristics of the graph of the polynomial function based on the degree of the polynomial and the leading coefficient. We're going to use factoring, which I said. We're going to identify the zeros and their multiplicities and what that does to the graph. We're going to determine the end behavior. We're going to talk about the degree and the turning points. We've done it in the last video. We're doing it again here, but now in the actual graph itself. And then we're actually use the intermediate value theorem that in Calculus 1 we actually go over quite a lot and explain where it comes from and prove what we accept as true here. So the first thing you want to do is to kind of refresh your factoring. So if for some reason you haven't had a chance to factor much or you just need some practice, I will put some practice of factoring of polynomials, quadratics in particular, into the Canvas shell, or you can just do a search on the internet that says, hey, give me practice with answers of factoring polynomials. So if we're asked to factor, and one of the most important things you'll ever get out of factoring polynomials is a U substitution type of situation. So we're going to say let U equal, and we let U equal, if it looks like a quadratic, this is what we call a reducible to quadratic. If it looks like a quadratic, it has three terms, and if I take the variable right here in the middle and I square it and I get the variable on the first position and the first term, then it's probably a reducible to quadratic. So I'm going to let U equal x squared. Then U squared is x squared squared, which gives me x to the fourth. So then this, using a U substitution, becomes U squared minus 5U plus 4 is equal to 0. And that's much easier for us to consider factoring. We're going to have U minus 4, U minus 1 is equal to 0. And so we have U is equal to 4 and U is equal to 1, but we're not solving for U, we're solving for x. So we have x squared is equal to 4 and x squared is equal to 1. So we end up with x is equal to plus and minus the square root of 4, which is 2, and x is equal to plus and minus the square root of 1, which is 1. Similarly, if I wanted to go back and put this as x squared here, I could have done x squared minus 4, the quantity squared, and then x squared minus 1, the quantity, or x squared minus 4, and x squared minus 1 is equal to 0, not quantity squared. This becomes x minus 2 and x plus 2, and the second grouping becomes x minus 1 and x plus 1. So you can see I did it by factoring, and if I set each one of these factors equal to 0 and solve, I'm going to get the exact same values as I do here. Or I went ahead and set the factors equal to 0 and solved, and then did the back substitution. I put what I said what U was back in, and then I solved for x. Either way is totally fun. It just depends. And if you're asked to factor, which is that one here, or if they're asked to find the zeros, which is that. That's similar but different. Okay. So on these, I'm not asked to do anything other than factor. So the only thing that's common between these two is 3. So a 3 will factor out, leaving me x plus 6. Here, a 2 and an x squared will factor out, leaving me 2x squared will factor out, leaving me x minus 4. This one is I'm going to try to do by factoring by grouping. So I'm going to look at these first two terms, and I realize a t squared is common, so I'll factor that out, leaving me t plus 6. Out of these two terms, I'm going to factor out a negative, because there's a negative there, so negative 2, t plus 6. Now, this and this are the same, so I will factor it out, leaving me t plus 6 coming out front. A t squared and minus 2 is left over, t squared minus 2. Now, the second grouping actually can factor some more. It's just not going to give us nice numbers. It is the difference of squares, so it's going to be t minus the square root of 2 multiplied by t plus the square root of 2. Because if I see something squared minus something else, which may not look like it's a square, will become the square root of t squared, which is t, minus the square root of 2, which is 2, and then the square root of t t squared, which is t, and then plus the square root of 2, which is there. So you can actually factor a difference of squares if it's not even a perfect square on the numeric value. So here's one where I'm looking for two factors that add up to 10 because it's a plus. I know it's an add, so it's going to be w minus 5 multiplied by w minus 2. And I can see that if I multiply this back together, I'm going to get 10, and add these together and I get 7w. All right, and so this one I have 2y and y. And I'm just going to do the guess and check method. The only way I can get to 6 is, well, there's a couple of ways, 1 and 6 and 2 and 3. Now I need to get a combination in which when I put the numbers here in these two positions, I'm going to get a negative. So if I look at my two factors, one of these is positive and one of these is negative. But I need to put my factors here in such a way that when I do 2 multiplied by this number and I do y multiplied by this number, I get a positive y because that's what my middle term is. So I'm going to use a positive 2 here and a negative 3 there. These two multiplying give me negative 6, and then 2 times 2 is 4, so 4y positive minus 3y gives us that middle term of y. Nice refresher. So the fundamental of theorem of algebra states that if you have a polynomial of degree n, which is strictly greater than 0, so we're not talking about a constant, then the polynomial has at least one complex 0. And you're like, what? That's okay, don't worry about it. We can use this theorem to say that basically that the polynomial of a degree n, where n is greater than 0, has at least one non-real 0 number and then has exactly n linear factors. So what does this really give us? This gives us the fact that as long as my degree is bigger than 0, every single polynomial will factor, but some of the factors that we produce will not be necessarily real numbers. But they will all factor into we'll have as many zeros as there is the degree. Some of those zeros may not be real numbers. That's what this tells us. So we can factor it. And it'll be factored into this many terms. So if we take a look, or factors, not terms. If we take a look at this, here is degree 2, and we ended up with 2 factors. Here's degree 2, we ended up with 2 factors. Here's degree 3, we ended up with 3 factors. And some of these, like this one, are not nice numbers when I solve for it. Here, I ended up with, and you're like, wait a minute, that doesn't look like 3 factors, but there are 3 factors here. This is 1 factor, and then x equals 0 is 1, then x equals 0 a second time is the second factor, is the second, or in this case, the third factor. So we will have the ability to factor every single polynomial that we come across. Just some of them, when we factor them, will not have real numbers. That's what the fundamental theorem of algebra states for us. Okay. And then the next question is are the zeros of our polynomial always the x-intercepts? And the answer is no. The answer is no. Because, as an example, if I have y is equal to x squared plus 4, according to the fundamental theorem of algebra, I should be able to factor this. And I can. I'm going to set this thing equal to 0 and solve, and I get x squared is equal to negative 4. Because we're in the land of learning complex, we know this is going to be x is equal to positive and negative 2i. So that tells us, since we have complex numbers for the zeros, that our zeros are not x-intercepts. So the zeros are x is equal to 0 plus 2i in the complex form, and x is equal to 0 minus 2i in the complex form, but not x-intercepts. So yeah, you can find, and I found, fundamental theorem of algebra says I should be able to factor it, and I did. This factors into x minus 2i and x plus 2i. There's my 2 linear factors of x squared plus 4. I found the 2 zeros, plus and minus 2i. They are not intercepts. So when we talk about our polynomial being in factored form, this is what we expect it to look like. some leading coefficient gets factored off, and then we have x minus some 0 raised to maybe some power, and then an x times some other 0 raised to some power. So if I start out with, as an example, let's say I started out with x to the 4th minus 7x cubed plus 10x squared. Here's my polynomial. The first thing I'm going to do is factor out my greatest common factor, which is x squared, leaving me x squared minus 7x plus 10. And we know from up above this factors. And so we get x squared, x minus 5, and x minus 2. So if I do a comparison to what this is and what this is saying, that my first one is x minus 0, the quantity squared. And this number, the quantity squared, is this number here where they label it as p, which is the degree of that factor. The degree of the next factor is 1. The degree of the next factor is 1 because I only see it once. So now I have it in the linear factorization. That's what this is called, the linear factorization. So if I'm given a polynomial and I'm asked to find the x and y intercepts, first thing I'm going to do is set it equal to 0 and factor it, if at all factor. And it says first thing you want to do is do any common monomial factors. That's this. Monomial is the single x squared term in this case. Factor any factorable binomials and trinomials. So when I factored out this monomial, which is this x squared, I ended up with a trinomial, which gives me this. And then set each factor equal to 0 and solve for the x-intercepts. The y-intercepts are always easy. We like them. All you basically have to do is put in 0 and you're done with it. So I'm just zooming in. Let's start with the y-intercept. I'm going to set x is equal to 0. And so I have f of 0 is equal to 2, 0 minus 3, 0 plus 1, and 0 minus 6. And so I'm going to get 2 multiplied by negative 3 multiplied by 1 multiplied by negative 6. So this is negative 6, this is negative 6, so my answer is 36. This is the y part of the y-intercept. It is not, by the way, the y-intercept. The y-intercept is the ordered pair 0, 36. Now I'm going to do the x-intercepts. Since this is already factored, all I have to do is set each factor equal to 0. I'm not going to set 2 equal to 0 because that's a false statement. 2 never equals 0, so I don't have to worry about that when I'm trying to find my x-intercepts. So x minus 3 equals 0, x plus 1 is equal to 0, and x minus 6. I want to go right to the answer. X minus 6 is equal to 0, so I get x is equal to 3, x is equal to negative 1, and x is equal to 6. These are the zeros. They're not wrote as intercepts. Intercepts are ordered pairs, so it's 3, 0, negative 1, 0, and 6, 0. For this one, I'm going to go ahead and start with my y-intercept again because it's the easiest to do. So my y-intercept, x equals 0, f of 0 equals 0. So my y-intercept is 0, 0, which tells me that's also, when this happens, this is also one of my x-intercepts. Now to find my x-intercepts, I have to do the factoring. I'm going to factor out an x because they're all divisible by x. In other words, they all have x in common. That leaves me x squared plus x minus 20. Two numbers that are factors of 20 that have a difference of 1. That's 4 and 5. So x plus 5, x minus 4 is equal to 0. So I have x is equal to 0. X is equal to negative 5, and x is equal to 4. So my intercepts are 0, 0, just like here. I knew that was going to happen. I'm going to have negative 5, 0, and I'm going to have 4, 0. All right. So now I'm going to take a look at my next example. Again, I'm going to find my y-intercept. So f of 0. Well, this is going to give me negative 8, so it is 0, negative 8. Easy peasy lemon squeezy. Now, I'm going to do my x-intercepts. I'm just going to erase this so I can have space. My x-intercepts. I'm going to factor out a 2 this time, leaving me x to the 4th plus 3x squared minus 4. And this is kind of like our warm-up. It's like a u sub. So I'm going to say, hey, you know what? Let's let u equal x squared, then u squared is equal to x to the 4th. So I can rewrite this in a form that I'm more familiar with, which is 2. U squared plus 3u minus 4. So this gives me 2, and the factors of 4 that have a difference of 1, which is 4 and, or difference of 3, which is 4 and 1. So u plus 4, u minus 1. Now back sub, so 2. Let me actually go back in black. So I'm going to do it back in black. So I'm going to have 2 x squared plus 4 and x squared. I wanted to say u. Let me erase that. It should be x squared. X squared minus 1. So this becomes 2. And then I get x plus 2i, x minus 2i, because this is just like the one we talked about earlier. And then x minus 1, x plus 1. So my x-intercepts are, by the way, not these. X-intercepts will only be produced from these two because these are complex, which means not x-intercepts. But these produce x-intercepts. This is going to be 1, 0 and negative 1, 0. All right, now this last one, y-intercept first because it's easy, y-intercept. This is f of 0, negative 18, so I have 0, negative 18. X-intercepts, I'm going to do this by grouping. So out of the first two, an x squared is common, so I'm going to factor out an x squared, leaving me x plus 2. There's a negative between these two, so I'm going to factor out a negative 9, leaving me x plus 2. X plus 2 is common in both, so I'm going to factor that out, so x plus 2, leaving me x squared minus 9. This becomes x plus 2, x minus 3, x plus 3. So my x-intercepts are negative 2 from the first one. So negative 2, 0 from the first factor, 3, 0 from the second factor, and negative 3, 0 for the last factor. Now, we talked a little bit earlier, just a few moments ago, about multiplicities, where we talked about the 0 has more than one. It's actually when I had x squared factored out, there was an x equals 0, and there was an additional x equals 0. We call those multiplicities. So if we take a look at this example, this x equals 3 has a multiplicity of 1 because there's nothing there, so it's an assumed 1. And this produces x is equal to negative 2, and it has a multiplicity of 4. So when we look at the multiplicities of our factors will tell us the behavior of the graph at that 0 if that 0 is an x-intercept. So if you go out to Desmos or any of those things and you graph these, this is going to produce x is equal to negative 3, and this is going to produce x is equal to 1. So I don't have a graph with me, but I can tell you based on the fact that this is going to produce x squared, this is going to produce x, so my degree of my polynomial is 3. This is 1x squared, and this is 1x squared, so my a sub n is greater than 0. So I know that my end behavior is going to be down in this quadrant and up in this quadrant. I know since I have real numbers here that I'm going to cross or bounce at negative 3. I'm going to cross or bounce at 1. So what my graph, and my y-intercept, so we should do the y-intercept too, y-intercept. This is going to be 0, and you're going to pass at negative 9. So down here at negative 9, not drawn to shape, not drawn to scale. So this is what the graph looks like. So it's going to come up here, touch that, cross through there, come back up and cross up. And that's what that graph should look like. Now I'm going to do the next one. This produces x is equal to -5. This produces x is equal to 4. This produces x is equal to -1. My first term is going to give me a positive 1x to the third. The next one is going to give me a positive x. And the last factor will give me a positive 1x squared. So I get x to the 6th, looks like. And my a sub n is greater than 0. So this is greater than 0 and n is 6. So I know that, I have an up in this direction and up in this direction. I know something's happening at -5. Something's happening at -1 and something's happening at 4. Now my y-intercept, when I put in 0, I'm going to get 0, comma, I'm going to have a 5 raised to the third power multiplied by a -4 multiplied by 1. So 5 raised to the third power is 125, and then multiplied by 4, it's a large number. Well, magnitude, it's large. Since it's a negative number, it's actually quite small. So 125 times 4, that's a -4, 500. So my y-intercept is 0, comma, -500. So my graph here, by the way, will not be drawn to scale. So I'm going to say this is -500. Now, what this graph will look like. Since I'm going to start up here, I'm going to come and I'm actually going to kind of do a slide right there. I'm going to come back to the -1. I'm going to touch and bounce, and I'm going to come back through here, and then I'm going to go like that. And that's kind of what that graph is going to look like. You can confirm that, but go and put that on Desmos. And then this one, I'm going to start with my x-intercept. So I get 0 for the first factor, 4 for the second factor, and -4 for the third factor. I'm going to get an x cubed term. I'm going to get an x term. I'm going to get an x term. So I'm going to end up with x to the 5th. So my n is 5. My leading coefficient a sub n is greater than 0. My y-intercept is 0, because whenever I have x is equal to 0, it's also my y-intercept. So I'm going to draw my graph here. So I know here is my x and y-intercept. I also have one at -4, and I have one at +4. Since my degree of my polynomial is odd, it's going to go down there in that quadrant and up there in that quadrant. And my leading coefficient is even, that confirmed, or my leading coefficient is positive. And so I'm going to need to come up here, cross, I'm going to bounce. Wait a minute. I'm going to come up and cross. Oh, I'm actually not going to bounce. I'm going to go slide on through that. So if you zoom in on your graph and it looks like it kind of slides through like that, comes back around and then goes back up. So that's what that graph looks like. You're going to find one that looks, well, obviously a lot smoother than mine. And then my last example here, I'm going to get x is equal to a +1/2 and x is equal to 4. Those are my my zeros, which are real numbers, so they will be the intercepts. I'm going to produce, my leading coefficient is going to be a -4 multiplied by 2x raised to the 2. And then I'm going to have an 1x raised to the 3rd. So you can see my degree of my polynomial is 5, and my a sub n, when I multiply this through, this will be a -4, this will be a +4, and that's going to be a +1. So my a sub n is negative. So that's going to be less than 0. So if I look at my graph here, since I have a degree 5 and my leading coefficient's negative, it'll be up in this quadrant and down in this quadrant. So I have a positive, I need to find my y-intercept in a minute. I have a +1/2 and a +4, my y-intercept. If I put in 0, I'm going to have -4 multiplied by -1 squared multiplied by -4 to the 3rd. Well, the -1 squared is going to be a +1, and so you're going to have a -4 times a -4 to the 3rd. So you have a +4 raised to the 4th power, because the negatives will cancel themselves out. And so my y-intercept is 0, 256. That's actually quite large. All right, so what's happening on this graph is that it's going to come, here is 256, not drawn to scale. It's going to come through there, touch this, bounce, come back through this, kind of slide through, and then go down. Okay, so what do you notice about the graphs when it's odd? If the multiplicity is odd, then you will cross at that x-intercept. And not only will you will cross based on what you, I don't know why that came in so big. You will cross based on what that is, the multiplicity. So if, say, the multiplicity is 1, it'll cross like a line. If it's 3, looks like a cubic at that intercept. And etc. And you can see from my graphs that when the multiplicity is even, then the graph touches and bounces off. You can see here, this was a cubic, and so it kind of had that little kind of horizontal slide there. You can see this was squared, the multiplicity was 2, so we touched and bounced. And this multiplicity was 1, so I kind of did a 1. So what I want you to do is I want you to go out to Desmos, put these in Desmos, and zoom in on the zeros. And you're going to see the shapes at those zeros better. So now that we've talked about it and you've looked at it, I want you to write what all of this is in your own words. Notice that they denote the multiplicity by the power of p, and that's why up above when we were talking about the linear factorizations, it was p1 for the first factor, p2 for the second factor, etc. So read through this, write this in your own words in a way that you are going to remember this. So this kind of wraps up what we just said. So here's a degree of 1, a degree of 2, a degree of 3. So what I want you to do is I want you to fill in the end behavior of this chart. So I'll start out with the first one. As x goes to negative infinity, my function goes to positive infinity. As x goes to positive infinity, my function goes to positive infinity. And that's what you need to do on the rest of this. Okay, so just fill in the end behavior. Here are the steps to graph a polynomial function. Look at the leading coefficient and the degree of the polynomial. What does that tell you about the graph? Think about that. Find f of 0. What does that give you? Find the zeros. Why is finding the zeros important? What does a multiplicity of the zeros do to help us graph? Find additional function values. Why? Well, I'll answer that one because we haven't done it yet. It kind of gives you a better shape of what's going on between the zeros, between the intercepts. And how many x-intercepts and how many turning points do you expect, and how do you know? So here we go. We're going to go through graphing this polynomial, given the steps above. Step number 1 says the leading coefficient. Okay, so a sub n is less than 0. My degree is 4. Well, what does this tell us? This tells us as x goes to negative infinity, my function is going to go to negative infinity. That's the chart up above I told you to finish filling out. As x goes to positive infinity, my function is going to also go to negative infinity. So now I know the end behavior. F of 0, well, f of 0 is 0, so this gives me my y-intercept. That's number 2. Finding the zeros, so in other words, I'm going to go ahead and factor this. So this is my first step, this is my second step, my third step. is going to be negative x to the fourth plus 4x squared is equal to 0. I'm going to factor out a negative x squared, leaving me x squared minus 4 is equal to 0. So I get x, negative x squared, x minus 2, x plus 2, that doesn't look like a 2 to me, is equal to 0. So I end up with 0, 0. I end up with 2, 0. And I end up with negative 2, 0 as my intercepts. So that gives me the zeros. The multiplicity. So the p on this one is 2. The p on this one is 1. So this is p sub 1. This is p sub 2. P sub 3 is 1. So this means I'm going to bounce. This tells me I'm going to pass. This tells me I'm going to pass at those zeros. I'm going to find some additional functions, and then I also know, based on this degree, that I'll do the number 4 in a minute, the extra ones. So number of turning points, so 4 minus 1 is 3 at most turning points. And that was on a previous videos in a previous section. And I know at most I'm going to have 4 intercepts. What I actually have is I do have 4 intercepts. This is just a repeating intercept. These are not repeating. So even though I only see 3 intercepts, there is 4 because this is a repeating, because my multiplicity on that is 2. Okay, so now I'm ready to graph this lovely thing. Boom, boom. So I'm going to go through 0, 0, and I know I'm going to bounce. So I'm just going to put a little b there to remind myself I'm going to bounce there. I'm going to go through 2, so I'm going to go to positive 2, and I'm just going to put a little p for pass. And I also have negative 2, so I'm going to put in negative 2. And I'm also going to put a p for pass just to remind myself that I'm going to pass through those. Like, I don't have to put that on the graph. That's just for me. That's just housekeeping purposes. And then I'm going to look at number 1, and it says, hey, I'm going to go in this direction and this direction. So I might choose f of 1. So f of 1 is going to confirm what I think the graph looks like. What I think the graph looks like, it's going to go through here and pass. It's going to come back down to this 0, bounce, come back up, and then go back down again. So this is what I'm expecting the graph to look like. So I'm going to choose f of 1 and see if I have a positive answer, because I'm expecting it to be positive, because f of 1 would be right here, and I would expect this to be positive. So I'm going to put in 1, and I have negative 1, so negative 1 to the 4th plus 4 multiplied by negative 1 squared, which gives me negative 1 plus 4, which is positive 3. Oh, well, actually my graph is right, but it just doesn't go out. It goes up a little bit higher than that. So I'd actually go up to positive 3. So it's actually going to go kind of up like that. Now, if I put in negative 1, f of negative 1, I'm going to get also a positive 3. Actually, I'm going to not get a positive 3, am I? Yeah, I'm going to get a positive 3 on that one too. So let me change this side of the graph. So this is actually going to go up to 3 as well. And so you can see why it's kind of important to choose some additional points to kind of get a better shape of the graph. All right, so I am going to have you do these next ones on your own following these steps, and then I will give you the answers. Welcome back. The first one is a sub n is negative, and my degree of my polynomial is 2, 4, 6, 8, 6. So that tells me as x goes to negative infinity, my function will go to negative infinity. As x goes to positive infinity, my function will also go to negative infinity. So I'm going to go ahead and start the graphing process, and I know I'm going to go down in this direction and then down in this direction. The next thing is the 0, so I'm going to do f of 0. Well, this is going to give me 0. So That tells me I already have one of my x-intercepts or y-intercepts. And that's because I have 0 right here. So I have 0 times all this other stuff, so I know that 0 is going to come out. So that's number 2. Let me see. Number 3 is the finding my 0. So it's already factored for me, so that's nice. The first one is going to give me 0, 0. This gives me 0, 0. My p sub 1 is 1. This one is going to give me negative 1, comma 0. My p sub 2 is going to be 2. This is going to give me 1, comma 0. My p sub 3 is equal to 3. And this last one is going to give me 2, comma 0, where my p sub 4 is equal to 1. This is a pass. This is a bounce. This is, oh, that shouldn't be 3. I said 3. No, it's 2 because of this as being 2. So that tells me that's a bounce, and this one's a pass. So I'm going to go ahead and put all of those things in there. So I'm going to come over here, and I've got 0, 0, and we know 0, 0 is a pass. We have negative, I'm going to make this negative 1, so this is negative 1. Right here, and that's a bounce. We have a positive 1, so we'll make this positive 1, and that's also a bounce. And then we have 2, the number 2, so here's where 2 is, and it's a pass. Okay, so I know number 4, I'm going to get a couple of points. I don't know what I'm going to get, but I'm going to get a couple of points. And then number 5, so if my degree is 6 minus 1, which is at most 5 turning points, at most turning points. I am not guaranteed that, but I will have at most. Okay, so even if I don't get any extra points, I know that I'm going to come up from here. I'm going to come up, I'm going to go through this, and it's a bounce. So I'm going to touch and bounce back off. I need to go back up to this, which is a pass. So I'm going to go through, and then I'm going to come back to the number 1. I'm going to touch and bounce. Then I need to go back up and then come back down, and I need to pass. So it's going to look something like that. And then if I like to know how far down it goes between negative 1 and 0 and how far up it goes between 0 and 1 and etc., then I would find f of negative 1/2, because it's about halfway between, f of 1/2 and f of 1.5. So that's how I would do that. So here is the last example. So go ahead and put this on pause and see where you are. Okay, so for the first part, we know a sub n is greater than 0 because that's the 3 right there. N is equal to 3, so that tells us as x goes to negative infinity, my function will go down to negative infinity. As x goes to positive infinity, my function will go to positive infinity. So we're going to graph at least that part of it. So down here in this quadrant, we're going to go down. In this quadrant, we're going to go up. Okay, the next one I'm going to put in 0. So f, or in this case h of 0, is going to give me 4. So my y-intercept is 0, 4. So let's put that on there. 1, 2, 3, 4. So here's my y-intercept. Now, if you factored this by grouping, you would have factored an x squared out of the first group, which gave you 3x plus or minus 2. If you factored out a negative 2 out of the next grouping, so you get negative 2, and you're going to get 3x minus 2. And so we get x squared minus 2, and then 3x minus 2. We know this, if we set this thing equal to 0, we're going to get x is equal to positive negative square root of 2. And this is going to give us x is equal to positive 2/3. So my intercepts are negative square root of 2, 0, square root of 2, 0, and 2/3, 0. Going out to number 5 is at most 3 minus 1, which is 2 turning points. Square root of 2 is bigger than 1, but less than 2. So here is 1 and here is 2. So the square root of 2 is somewhere in here. Negative square root of 2, if this is negative 1 and this is negative 2, square root of negative 2 is somewhere in there. The multiplicities are p sub 1 is equal to 1, p sub 2 is equal to 1, and p sub 3 is equal to 1. So they're all going to pass. So at 2/3, so 2/3 is about right here, we're going to pass here, and pass here. So let's connect our dots. We're going to start down here, go through and pass, go up to that y-intercept, go back down to 2/3 and pass, come back up to positive square root of 2 and pass and go back up. Now, the point that I would probably want to do is this one. So for number 4, let's do f of 1. So I get 3 minus 2 minus 6 plus 4. So I have 3 minus 2, which is 1, minus 6 is negative 4. Is that right? So negative 1. So the negative 5 plus 4 is negative 1. So the 0.1 comma negative 1. I actually made it come down further than it needs to. So let's go ahead and just kind of change that to make it only come down to 1. I just go and ham on it, I guess. So it's going to come down to 1, and so that's what that's going to look like. So that gives me a better shape. By doing that, a couple of points on the graphs, it gives me a better shape. Okay, so now we're going to be asked for a polynomial, find a polynomial with the least degree. Okay, so these are the things that I know. This first one is going to produce x plus 3. This intercept is going to produce that factor. This intercept is going to produce the x plus 1, and this intercept is going to produce the x minus 3. So this is what I think I have: x plus 3, x plus 1, and x minus 3. What I don't know is what my leading coefficient is. And the way I'm going to do that is this is what I think my function is. And the way I'm going to figure that out is I'm going to use this intercept. What I know is that when I put in 0, 2 better come out. So let's set this thing equal to 0, or I set it equal to 2. So 2 is equal to a 0 plus 3, 0 plus 1, and 0 minus 3. So 2 is equal to, well, this multiplied, so 3 multiplied by 1 is 3, multiplied by another negative 3 is going to give me a negative 9a. So what my a is going to be negative 2 over 9. So my final answer is f of x is equal to negative 2/9, x plus 3, x plus 1, and x minus 3. This confirms that I have a degree 3. Here's my degree 3, an up and a down type of situation. And I have a negative coefficient. That's what I found it to be. And that confirms the end behavior. Let's take a look at this next one. We're going to do the same kind of thing. This gives me x plus 3. This 0 gives me x plus 2. This 0 gives me x minus 3. And this 0 gives me x minus 4. So I have f of x is equal to a x plus 3, x plus 2, x minus 3, x minus 4. I'm going to use the fact that it is crossing at 0, negative 3. That means negative 3 is equal to f of 0. So negative 3 is equal to a 0 plus 3, 0 plus 2, 0 minus 3, and 0 minus 4. So this is negative 3 is equal to 3 multiplied by 2, multiplied by negative 3, multiplied by negative 4, multiplied by a. And the only reason I'm not multiplying this through is because when I divide both sides, I'm going to divide both sides by 3, 2, negative 3, and negative 4. So 3, 2, negative 3, and negative 4. These cancel, and it just makes my multiplication a little bit easier for me because I don't have my calculator with me. So I have 1 over, I'm going to have 6 times negative 4, which is 24. Negative 24 is equal to a. So I have f of x is equal to negative 1 over 24, x plus 3, x plus 2, x minus 3, and x minus 4. And that is my answer. Okay. So on this, they're asking us to sketch the behavior given the information that's given to me. These are my zeros. I have a degree 3. And as x goes to negative infinity, it's going to go to negative infinity. As x goes to positive infinity, it goes to positive infinity. So that tells me that at -2, -1, and 4, I'm going to pass. It's going to come down in that quadrant and up in this quadrant. Gonna go something like this. There's my graph. So degree 4, okay. As x goes to negative infinity, this goes to negative infinity. As x goes to positive infinity, my function goes down. So I'm going to go down in this direction and down in this direction. I have 0, I have -5/2, and I have 3. One of these needs to touch and bounce. One of these has to have, since I only have three zeros given, and they're all real, that means one of these is going to have a multiplicity of 2. It doesn't matter which one. Choose one of them. I just make sure I need to get a degree 4. So I might decide to have the first one be the multiplicity of 2. So I'm going to come up to the -5/2, touch, bounce, come back to this one, cross, come back through. So that's what I could write it as. Or what if I wanted to have my 0 as a multiplicity of 2? So -5/2 and 3. It could look like this. It'll come up here, touch, bounce, come back, and then go back down. So either one of these are valid, or you could have had the multiplicity of 3. It doesn't really matter. All right. So here is my zeros. I'm a degree 3, and I have 3 zeros. These two are complex numbers. So these two tell me that even though I get a 0, I'm not crossing the x-axis anywhere on those two, and I'm going to be crossing at -4. So these two are not going to give me intercepts. At -4, I'm going to cross, because it has to have a multiplicity of 3, because I have 1, 2, 3 zeros, degree 3. So I have to cross there. As x goes to negative infinity, the function goes down. As x goes to positive infinity, the function goes up. So it's going to look something like this. Or it could look something like this. That's all I know. And you're like, where are you getting this? Where are you getting this kind of corner, this kind of turn? That's because I have complex numbers. Those complex numbers are going to kind of give me a little bit of a turn somewhere, but it's just not crossing the x-axis. All right, quadratics. We know exactly the location of the min and the max. We know exactly where it is, right? All we have to do is find the vertex. All the other polynomials, not so easy. So we have to use more advanced techniques from calculus. So in calculus 1, we will spend time finding the location of the extrema. In this one, we're just going to use approximations. Like I can tell you it's approximately just based on the graph without needing any real kind of technology, actually. What I know is that in between two crossing points, or a touch and a bounce, if I come and I cross, somewhere in between there, I'm going to have a maximum. In this case, somewhere in between these two, basically I come down and I go back up. I have to come down and touch back up. Somewhere in between this 0 and this 0, I'm going to have a minimum. And since this one crosses and it crosses here somewhere between them, the shape of this tells me I have to have a maximum between 4 and whatever that is, 5 and a bit. Okay? So who will have globals or absolute? And the only ones that are guaranteed to have it, is when n is even. When n is even, I will have an absolute max or an absolute min. In this case, where my leading coefficient is negative, I will have an absolute or global maximum. If my leading coefficient is negative, I will have an absolute or global minimum. Using your calculators, sketch the graph and estimate the max and min. So if I had my graphing calculator out, I'm going to sneeze. I don't want to sneeze. I don't want to sneeze. I would type in my graphing or Desmos. I'd use Desmos. I would type in x to the third, and I have minus x, and I have plus 1. And this, if I tried to factor it, which we are going to learn how to factor this, is going to produce one real number intercept, and we will learn how to do that, just not in this video. And it's going to cross about negative 1.3. And then the other factors are not real numbers. And I know on my y-intercept to the very minimum, I know that by saying, hey, that's the only thing that doesn't have an x attached to it. It actually looks something like this for that graph. And you're like, how am I supposed to do that on the test? Well, I'm going to show you how to do it, not in this video, but I'm going to show you how to find these values that are not so easy when I factor. Okay, so now I'm going to do my next one. If I had my Desmos, I would type in a negative x raised to the 5th plus x raised to the 3rd minus x and minus 2. And this graph, we're going to cross about, it looks like about negative 1.2. My y-intercept is negative 2, so this is negative 0, negative 2, just like this is 0, positive 1. And then what this graph kind of looks like, this is kind of a cool graph. It comes and it kind of does this kind of thing. Kind of wants to go do this, and then it kind of evens out, and it kind of does that, and then it kind of does this kind of thing. So what this is telling me right here, because I have some kind of turns, sort of, like I have horizontal slides, that means I have some complex numbers going on. Okay, and then our last one, I can at least start the factoring process. Like I can factor a cubic all day. I'll factor out an x first. That leaves me x to the 3rd plus 1. This becomes x plus 1, x squared minus x plus 1. That's what that factors to. This is complex. You'll get complex numbers there. So what I know is that I will cross at 0. I will cross at negative 1. That's at least I know. I know the behavior. It's going to be up in this direction and up in this direction. Here's y and here's x. You all should be putting x and y on your axes. Don't be like me. Don't be a me. Be a you and do it correctly. So I'm going to have x raised to the 4th. I'm going to go out to my Desmos, and then I'm going to have plus x. And so what this graph looks like is it comes down, it crosses, it comes back up, it crosses. Kind of does this weird little slide there. And so this tells me right there that I'm somewhere in there, I'm going to have some complex numbers as solutions. All right, intermediate value theorem. What is the intermediate value theorem? Well, if we're asked to evaluate this, all I want to know is at 1 and negative 1. So let me put this on this graph. So I'm going to put negative 1 into my function. I'm going to put positive 1 into my function. That's what this says. If I do f of negative 1, this is going to produce a negative 1. This is going to produce a negative 4. This is going to produce a positive 1. So my answer, what I care about is, well, let's go ahead and just graph it. I'm going to get positive 4. So positive 4 comes out. So I'm going to come up here to positive. Here's 1, 2. Oh, well, we're going to do this. This is 4. So here's my output. Now I'm going to do f of 1. So f of 1 is going to give me 1, negative 2, and then I'm going to get positive 3. This gives me a negative 6. So I'm going to come down here, 1, 2, 3, 4, 5, 6. So here's my ordered pair 1 comma negative 6, and here's my ordered pair negative 1 comma positive 4. Because this is a polynomial, I didn't mean to do that. Because this is a polynomial, this tells me that my, how do I make that? Okay. Let me make this much smaller. Just want to get rid of some of that stuff. Okay. Negative 6, that's a terrible negative 6. That's positive 1. Okay. Because this is a polynomial, I should be able to draw this graph without picking up my pencil from left to right. So I know my leading coefficient, a sub n, is positive. I know that my n is 3. These two combined tells me I'm down in this direction and up in this direction. So even if I didn't know any of that information, what I do know, since this is a polynomial, is somewhere between negative and 1, because the outputs change from positive to negative, I had to have crossed. And in fact, I know I happened to cross at 0. But had I not known that, the intermediate value theorem would have told me that I had to have crossed. So let's take a look at g of negative 4. I put a negative 4, I'm going to get negative 4, the quantity squared. I'm going to get negative 9, and then I'm going to get negative 1, the quantity squared. So I'm going to get 16, a positive 16, because a negative 4 multiplied by negative 4, a positive 16 times a negative 9 multiplied by a negative 1 squared is basically going to be a positive 16 multiplied by negative 9. And this gives me a negative 144. Now, if I do g of negative 2, I'm going to have negative 2 squared, negative 7, and positive 1, the quantity squared. This is a lot easier. This is negative 28. So what I know, obviously I'm not going to draw this to scale. I'm going to come over here and let's assume this is negative 2 and let's assume this is negative 4. So when I put a negative 4, I'm way down here at negative 4, negative 144. And then I have a negative 2 and I get negative 28. Let's assume this is negative 2, negative 28. Because my outputs are both negative, I have no idea whether or not I actually have a value between these two, a 0 between these two. I have no idea. So the intermediate value theorem, if the outputs are the same on both sides of the interval, so the interval from negative 4 to the interval of negative 2, if I choose a value negative 4 and negative 2 and their outputs are both negative or they're both positive, then I don't know. I have no idea. I actually do know it is negative 3, but it's a bounce. So I'm not crossing because negative 3, this produces x is equal to negative 3. And my p is 2, so this is a bounce. So the intermediate value theorem will tell you whether or not you have a 0 that crosses. It doesn't tell you if you have a 0 that bounces. So it's great, but not so great all the time. So that's what the intermediate value theorem is it does help us, especially in the next section, next couple of sections, when we start trying to factor and figuring out whether or not I'm finding zeros, is the outputs have opposite signs. That means there has to be a 0 between those two numbers you chose. That's what the intermediate value theorem is, and that is it for this video.